Hello, in this video we are going to continue our discussion on binary search. If you haven't watched the video on binary search, this will be a good time to do so. This video is going to discuss the most commonly used code for the implementation of the binary search. So as you remember, the binary search consists of finding the middle of a collection, typically an array that has indexes. So we find the middle element. Then we compare that with the value that we're looking for. If there is a match, we stop the search, obviously. If there is not a match, then we need to decide, now that we know the middle point of our collection, we need to decide in which half, the first half of the second half of the collection, is most likely to contain the value that we're looking for. So once we pick one of those half, we repeat the process. In other words, we take that half, we find the middle of that half, we compare the middle element with the value that we're looking for. If there is a match, we stop. If there is no match, now we need to decide which halves of that half, which means a quarter. So every time we're shrinking the space by 2. So this is how the code works. Essentially, in Java, this would be a method, we call it bin search, that takes 2 parameters. One is what we call the list, which is a basic array of integers. It could be an array of objects, it could be an array of strings, an array of any values. And then this is what the object in this case is an integer value, and the key is a generic name. And again, the value that we're looking for could be any object. Notice that this method is going to return an integer. So that may be a little bit of a surprise. Perhaps we were expecting to see something that returns true if we found a match, false otherwise. I'm going to explain why is that we return an integer, okay? So the first part is to identify 3 very important indexes. Those indexes are the value of the lowest index on the connection, the value of the highest index in the collection, and the value of the index in the middle of our collection. And obviously those are integers independent of what kind of values we have on the collection. Then we initialize them, and of course the lowest values for low at the beginning is 0. That's the lowest index in Java. And keep in mind that this is the index of the leftmost element in our array. So it's the first one, index is 0. On the other hand, high is the highest possible index in our collection so far. And at the beginning, that will be the last element in our array. And in order to calculate that, we can use Java and determine the length of the array and subtract 1. And that is because we start with index 0. And obviously, we don't know what the value of the middle element is, so we're going to initialize that to 0. So we initialize the 3 indexes to the proper values at the very beginning of the collection. So right now, the list contains all the elements. And again, think about big data. Think about this array called list having 150,000, 500,000 elements, something like that. Then we're going to use what is called a Boolean flag that we call found. This is a flag in the sense that it's going to have only 2 values. It's either on and off. So it's going to be false or true. So right now, I'm setting found to false because I don't know whether or not there is a match. So the logical assumption would be that found is false. So remember the steps. The steps is to find the middle, compare the middle element, okay? And then if that is not a match, we need to decide which half we need to take and then to repeat all that. So all those steps are here, okay? I'm going to explain one by one, but I want you to understand that all those steps are here. But I don't know how many times I have to repeat the same technique, how many times I have to split my collection by 2. So let's start here, and then we'll analyze the while loop. So what you see here is the first step is to find the value of the index that contains the middle element, the element on the middle of my collection. So now that I know the value of the lowest possible index, the value of the highest possible index, I add those and I divide by 2. This is an integer division. So this is going to give me an integer. So now I have the index of the element located in the middle of my collection. And at the very beginning, this will be the element exactly at the middle of my 250,000 or 500,000 elements that I have. The next step is to take a look at the value located at this index and see if that matches my key. If that matches my key, then I have a success, right? I have a match. So I'm going to compare key with the middle. Now notice that here I'm using the equal operator because my collection was defined as a collection of integers. If this were, for example, objects of the string class, or an object containing student information, or an object containing information about any other object, then I wouldn't be able to use the equal operator. I would have to use the equals method, and I would have to have defined that previously. Okay, so here I'm using this operator because I'm using integers. So this is either going to be true or false. I have a match or I don't. If there is a match, I'm done with my search. I found it, right? And I know where it is. It's exactly in the middle of my collection. So I'm going to say found is true. And we'll see how this impacts the conditions in my while loop. Now, let's assume, and that would be most of the case, right? When we look for something, we don't find it the very first time around. So if you're looking for a word in a dictionary and you open the dictionary, which is in alphabetical order, you don't find the word right away, okay? So most likely this is not going to happen. So this statement most likely is to be false at the very beginning. If it's false, now I have to make a decision. Which of the two halves, let's assume this is a dictionary, which of the two halves of my dictionary contains the word that I'm looking for? Remember, this array is sorted. So in the case of integers, the integers value are in order. Let's assume increase in order. So if the middle element doesn't have the integer that I'm looking for, now I have to decide which of the two halves in my array of integers is likely to contain the integer that I'm looking for. Could be the first half, meaning values which are less than this value in the middle. And that's exactly what I'm doing here. What I'm doing here is saying, okay, let me find out if the value that I'm looking for is less than the value that I just looked up that is located on the middle. In other words, let me decide if key, the value I'm looking for, is likely to be found on the first half of my sorted array. And again, this could be true, this could be false. Think again, looking up in a dictionary. So if you take the first half of the dictionary, you know the English alphabet, so you can tell immediately whether the element, the word, the definition that you're looking for is in the first half or in the second half of the dictionary. That could be true, that could be false. If it's false, notice that I don't need to check for another condition, because by default, if it's not the value in the middle and it's not in the first half of my array, then it has to be in the second half of the array containing values which are greater than the value in the middle. Okay? Again, if you are confused at this point, you should watch the video on binary search and then come back to study this code. So here are, in summary, the three possibilities. Either I have a match, which is the element of the middle. The element is likely to be in the first half of the array. The element is likely to be in the second half of the array. Now, what happens if I don't have a match and this statement happens to be true? Okay, well, now I need to repeat the process because I haven't found a value, right? I haven't arrived to a final determination of my search. And now I need to readjust. What does it mean, readjust? Readjust means that now I can say, oh, if this statement is true, meaning that the value I'm looking for is likely to be in the first half of my collection, then I don't need the second half of my collection. And in order to do that with my code, what I need to do is to readjust the value of the indexes that I call high. Remember, we start high, assigning to high the value of the rightmost position, the last element. Now I know that the values between the middle and the last element are not likely to contain the value that I'm looking for. Therefore, I can discard, I can ignore all the values in my collection between the middle element and the last. So in order to do that in my code, what I need to do is to readjust the value of high. Okay, I have to give high a lower value that has to be less than the value in the middle. Why is that? Well, because, again, let's repeat what I did. I decided that the value that I'm looking for is on the first half. That means that it's not the value in the middle, and it's not the value between the middle element and the last element. So I need to decrease the value of my index that I call high by saying it's going to be middle minus 1. By the way, middle minus 1 is the index to the left of middle. So my collection now goes from 0, because I haven't changed low, to middle minus 1. I have eliminated half of the data from middle to the length minus 1. Now what happens if this statement is false? In other words, the value that I'm looking for is not likely to be on the first half. Then I'm going to be in the else, and the else again means it's not the element on the middle, it's not likely to be on the first half. Then my only possibility is that it's going to be possibly in the second half, between middle and the last element. If that is the case, I decided that it's going to be between middle and the last element, then I need to change the value of the index that I call low. Remember, low starts at 0. Now, if I'm here, that means that the value that I'm looking for, key, is not likely to be in the first half, in the half that starts with index 0 and goes to value middle. So I can discard, I can eliminate all those indexes between 0 and middle. And the new value of low is middle plus 1. So I'm going to repeat the loop. And essentially, what I'm going to be doing most of the time is deciding which half is most likely to contain the value that I'm looking for. The collection that has values less than the one in the middle, or the collection that has values with values larger than the one in the middle. And every time I make that decision, I need to readjust one of the values of my indexes that I call high and low. Now, if you analyze this code, you're going to see that every time that this statement is true, I update the value of high using a smaller value for the index. Every time that I decide that the value is going to be in the second half of my collection, I increase the value of low. So as I repeat this technique, the value of the index I call high decreases, the value of the index that I call low increases. So if high decreases and low increases, you can visual that, right? 5 is getting smaller and smaller, low is getting bigger and bigger, so they're getting closer to each other. That's going to be important to understand when we analyze the loop. So now let's talk about the loop, because remember, we need to repeat this technique, all this step, finding the middle, comparing the value in the middle, and deciding which half to take, but readjusting the values of high and low many times. I don't know how many times, so I'm going to use a while loop. And the while loop is going to have two conditions. Why is that? Well, let's think about what happens in real life. When you're looking for an object, you start in a random place, you start looking for, and as soon as you find it, you stop. So I need one condition for my while loop that says stop as soon as you have a match. Stop as soon as this condition is true. So that's why I'm using this Boolean flag, call found, and initialize it to file. So notice that when this statement is true, I have a match, then I immediately reset the value of found to true. So my condition should be not found. As long as the item is not found, as long as there is no matches, I should continue to search, which is what happens in real life. Initially, the value found is set to false. Not false is true. And because it's true, the while loop will iterate. Eventually, it is possible that found is going to be reset to true. And when that happens, this evaluates to false. Not true is false. And because the condition is false, then the while loop will stop. That's the first condition. What else do we stop our search? Let's think again about what happens in real life. In real life, You keep looking and looking and looking for your lost wallet and your lost keys, and eventually you say, oh, it's not on my room, or it's not in the dining room, or it's not in the car. You search everywhere that is possible, and you didn't find the value. You didn't find what you lost. So we need a condition that is similar to that, a condition that reflects that phenomenon. A condition that says, I have looked at every possible value in the array and there are no matches. Okay, so how do we translate that to code? Well, that's where the indexes come to play. Remember that I said that every time that we choose a half, we need to update either the value of high, which represents the rightmost index at any given time, or we need to update the value of low, which represents the leftmost index at any time. Also keep in mind that these indexes are getting closer to each other. High is getting smaller and smaller, low is getting bigger and bigger. So they're approaching each other. So my condition is as follows. My condition is as long as low is less than or equal to the value of high. So let's think about what that means. That means that as long as the index of low is less than or equal to the index of high, that means that there are some elements in between low and high that needs to be inspected. There are some spaces in real life that I need to look for. The spacers are getting smaller and smaller because low is increasing and high is decreasing. Okay? So, as long as there is a space to look for, I need to do so. Let's take a look at the initial values. Low starts at 0 and high is the rightmost index, the very last one. So at the very beginning, low has the index of the very first element, high has the index of the very last element. Obviously, this condition is going to be true. Low is less than high. And I have said found to be false, not false is true. So these two conditions at the very beginning are both true, and because I have an AND, the entire expression is true, the loop will iterate. The loop will stop as soon as one of the two conditions becomes false. Remember, this is an AND. So as soon as one of these two conditions become false, the loop will stop. So the loop will stop as soon as we found a match, because not true is false, or as soon as low passes high. The value of the index represented by low becomes greater than the index represented by high. And that's a contradiction. And when that happens, that means there are no elements to look for. I need to stop my search and conclude that I have not found it. Notice that in these two statements, all I do is to change the values of high and index. I never change the value of true. So these two statements are going to simply say there's still some elements to be searched, continue the search, or eventually, hey, the value of low is greater than high, so stop my search. So those are the two conditions that I need in my while loop. Now, what happens at the end of the while loop? Okay, at the end of this while loop, I don't know exactly what happened. What do I mean? Well, I know that the while loop, if everything else is okay in my code, is going to stop. It's either going to stop because there is a match, because found is true, or is going to stop because I inspected every possible element that I could, and there are no matches. Low is greater than high. Now, I need to figure out which of those two conditions, right? One implies you have a match, the other one says you don't have a match. I need to figure out which of the two conditions made the loop stop. And this is why I have this if-else, okay? And that's my second use of my Boolean flag found. I'm gonna say at the end of my loop, found is either true or false. Either I found a match, found is true, or I didn't, found is false. This if-else, this statement, takes care of that. And it says, okay, if found, if we have a match, then I know what it is. And it's going to be the index in the middle, okay? It's not going to be high, it's not going to be low, it's going to be the index of the middle. Remember, the idea is to divide the space by 2 and take a look at the value of the middle. I never compare with the value that is on the first position or in the last position of my collection. I only compare the value that is on the middle. So if there is a match, the index is represented by middle. So that's what I return. If there is a match, then return the middle. But what happens if there is no matches? What happens if we didn't find it? Then the convention, because I'm looking for an index, is to return a value that will indicate we didn't find it. Now, we know that in Java, indexes in any array have to be integers and have to be values starting with 0. They cannot be negative. So I'm going to intentionally return -1, which will clearly indicate to me in some other portion of my program that this search failed. I could not find a match for key. This explains why this method returns an integer. Okay? Remember, maybe you're thinking, oh, the search should return true or false, but think about it. What if the search returns true? That's not very useful. Where is it in my collection? Where is the index of the element that contains the value that I was looking for? That's what I really need. I don't need to know true or false. I need to know the index so that I can maybe print it or modify it or delete it or do whatever I want to do. So what I really want is the location of the value that matches this key, the location in my array list, in other words, the index. So returning -1 in programming, in computer science, is a convention that says if you're searching on an array and you return -1, that translates to is not found. And you probably are familiar with some methods of different classes that return -1, and again, all of them are used to indicate failure. That is basically the code. Remember another thing, you may go into the internet and you may find different interpretations of binary search, different ways of formulating the code. This is a while loop, so this code could be rewritten using recursion. So if you're familiar with recursion, I encourage you to do so. And just to summarize what's happening in this code, let's go over the rules, okay? First and foremost, remember, the collection has to be sorted. The array has to be sorted so that it makes sense to talk about low and high and middle. Every iteration partitions the collections in half, and then every iteration requires only one comparison. Okay? So that is this part. Every iteration partitions our collections in half, and then we only have one comparison. We compare to the element of the middle. After that, we just simply decide which half do we want, and then we repeat the process. And we said because of this, because we are continuously dividing our space, the array, in half, that the expected running time, the average running time, is big O log 2 of n. In other words, the expected running time in a binary search is log base 2 of n, where n is the size of the collection. And remember, keep in mind, when you see this number, that n should be a very large number, hundreds of thousands, tens of thousands. So I hope that this code is helpful and that you understand how binary search works.